everybody, and thank you for joining the webinar today. Sorry about that few minutes after the countdown. We had a little bit of a hiccup to start the broadcast. So I wanted to first introduce Pete Winship. He is the Technical Product Manager for Teledyne CETAC and will be presenting the webinar today. The title is Rack Up Your Samples and Leave. Allow the SDX HPLD Sample System to handle your ICP-OES preparation and introduction for water analysis. Before I hand it over to Pete, just a couple items that I wanted to touch on. We have quite a bit of information that Pete is presenting today, so we are concerned about the time that we've allocated for the webinar, and we've decided that Pete will just follow up with anyone who has questions after the webinar through email. So please feel free to ask or submit your questions at any time during the webinar using the question feature, and we will get back with you on that. And the webinar recording will be posted to our website and our YouTube channel within the next couple of days. All right, and with that, I'd like to hand it over to Pete.
Thank you, Betsy. Thank you for the kind introduction. Thank you, everybody, for joining us today. My name is Pete Winship. I'm a product manager at Teledyne CETAC Technologies. One of the systems that I'm responsible for is the SDX HPLD system, which we'll go through on today's broadcast. So as Betsy gave the title of this presentation, so I will make a start. So first of all, I just wanted to go through a quick webinar agenda, just to take you through where we're going to go with this presentation. So to start with, I'm going to work through an idea of an analytical workflow for an ICP-OES analysis. So this is a sort of a general workflow that can be applied to pretty much any kind of sample, really. And I want to keep referring back to this through what we're discussing today about the SDX system, about waters analysis. So I'm going to start there, and I'll be referring back to the idea of a workflow. Then I'm going to go into the SDX HPLD system, what it can do, go through the different capabilities of it, and then go through a hardware tour. And then I want to take that and apply it to the analytical workflow and work through the automation of that workflow. So I'll go through that and what the SDX HPLD system can do for it. And then further from there, I'm going to apply it to an example of analysis of wastewaters. So that's the agenda for today. So I shall make a start on a workflow. So the analytical workflow. So basically, this is where everybody starts and ends for any kind of analytical process for measurement of elements, metals, trace elements, with an inductively coupled plasma optical emission spectroscopy system. And so you start with a sample. So as our sample here is highlighted in red on the left-hand side of the screen, and ultimately we want to arrive at data from that sample, as shown by the highlighted in green on the right. So this is the case for any and all analytical technology, analytical technique that we have. So from starting at our sample, for an ICP-OES analysis, our next step would be we might need to do a sample digestion if we have a solid sample, or if we have a sample that contains, let's say, a high level of total dissolved solids, etc. That might be the case, it might not be. We would highly likely need to do a sample dilution. And then if we are quantifying analytes of interest, then we're going to need to analyze these samples in relation to some calibration standards. So we need to prepare those. We would need some form of QC samples, so quality control sample as well, to basically give us quality assurance, quality control of our measurements, and also prepare some blank solutions. so that we cover all of our bases and we can arrive at good quality quantified data from our sample. So that the data that we get is representative of that sample in the first place. So that would be our next step. Once we've got these solutions, we've done this preparation, once we've got all of this in place, the next step would be we would then introduce these samples to our ICP-OES instrument. That might be done manually, or it might be done via some form of automation. Once we've introduced those samples, those standards, blanks and QCs to our instrument, we would then, those samples would be processed, and we'd move on to the next stage. We would have some sort of data output. So that might be a raw data output that we might then need to do some data processing on. And that, so we might have some data that we would drop into another software package, say something like Excel, or we might have, depending on your ICP system, we might have a direct calculated output. So our data output might be final quantified data, or we might want to do both. We might want to take that quantified data and the raw data, do our own processing, and end up with our data results. So that is a workflow. It's quite a simple workflow. Now, in an ideal world, we would stop there. Our data output would be the data in green. That's what we would want to get to. Unfortunately, we don't live in an ideal world, and there might be some issues with the data output, so which would take us on to the next step. So we might have a situation where we have had a QC failure. So our QC criteria might be that our QC samples might need to agree with a certain data level, a certain known concentration of analyte, for example. And our QC criteria might be that the QC data agrees within a certain tolerance. So let's say plus minus 5%, for example. And so many QC samples out of the total might need to meet that criteria, otherwise we'd consider the batch to fail. So that's one area to consider when the data has been generated. A calibration failure, so all of our samples, have they all fallen within the calibration range? Is the R² value of our calibration line, is it as close to 1 as we would like? Or is it not meeting a certain criteria there again? For elemental analysis with ICP optical, internal standards. So we might be running an internal standard as well to account for any variation in the sample matrix. And so we might be looking at that in terms of internal standard suppression. So if there is internal standard suppression, is that within a certain acceptable tolerance, or is it greater than that? So we then have to ask these questions. And if the answer to any of these is that the QC criteria doesn't meet what I set out, or the calibration is not what I want it to be, and I've got samples exceeding the top standard, if the internal standard data is suppressed, if any and all of these, if the answer is yes, then we might look to do a reanalysis. We might go, I want to reanalyze this data. I want to change certain things about the analysis. And then we go through the process again. So this is a very simplistic workflow. In terms of analysis with ICP-OES, there might be additional criteria to add to this. But in a nutshell, that is this process. And this is what I'm going to keep referring back to today. So I just want to go back to some of the areas of this workflow. So I'm going to start with sample dilution procedures. So for a lot of types of analysis and a lot of sample types in ICP-OES, sample dilution of the sample in some sort of low concentration acidic media is one of the most common ways of preparing a sample or a calibration standard prior to sample introduction and measurement. Now, I've certainly been in this position for a number of years. I spent a lot of time preparing samples, doing this dilution manually with a pipette. So it is very time consuming, this process of sample dilution. The more samples you have, obviously the longer it takes. But you don't just have your samples, you have your calibration standards, you have your blanks and your QCs, and the larger the batch, more likely the more of those standards and blanks and QCs that you need. Accuracy and precision. So if you're pipetting manually, doing dilutions manually, then again, accuracy and precision does come into this. And with the best will in the world, if you're incredibly careful, the more care you take in pipetting, more likely you're going to be adding more time in preparation. But because it is a manual process that you're doing physically, then there will be error associated with that repeat process of preparation, pipetting, diluting. In any laboratory, there is a cost of staff time for preparation time. That's a financial cost. It's also an effort cost, and it is a cost of somebody in a laboratory could be doing something else instead of spending the time preparing samples. And then, depending on the success of your analysis, this is thinking back to this workflow again, depending on that success, if an analytical batch fails, then you might be looking at doing a repetition of that batch, and again, so that there's the same amount of time to be spent again, preparing samples, diluting, etc. So that's sample dilution. That's something I do want to come back to. Is a repeat analysis necessary? So I've already noted a couple of things on this. So you might have a scenario here where you've got analyte elements that you're interested in your ICP optical analysis. In unknown samples, some of the analyte concentrations, they may exceed your calibration range. They may fall outside of your range and above your top standard. You might have, again, in unknown samples, something new that you're working with. Sample matrices may cause some sort of analyte suppression, and that might push your internal standards outside of tolerance. So again, that begs the question, do you need to repeat an analysis? Pipetting errors, accuracy, precision, all plays into how the quality of your analysis and whether you get the calibration lines that you want, the calibrations R squared as close to 1 as you want. So that plays into this. If the R squared is not what you want it to be, then that might bring about a repeat analysis. Something else to note here as well is that I refer to repeat analysis. Now, you might have a batch whereby you've had out of an analysis of maybe 100 samples, you might have 3, 4, 5 of those samples might have fallen out of calibration range. Now, I say a reanalysis, so you might be looking at what do I do about those 3, 4, or 5 samples. Now, that doesn't sound like a lot, but a point to make here is that a reanalysis is not just the samples that might not have passed your criteria. If you are going to do a reanalysis of a small number of samples, it's also a set of calibration standards, it's also the blanks to go with this, the quality control criteria as well. So it's never just 3, 4, or 5 samples, it's 3, 4, or 5 samples, plus all of those reagents, those solutions that need to be made up as well. So going back to this workflow, what I want to do going through the rest of this presentation is essentially to apply automation to this workflow and to show you what's possible to simplify this and remove as much effort as possible from it. So what I'm going to do next is I'm going to take the SDX HPLD system, so this is our SDX high performance liquid dilution system, and essentially bring it into this workflow. So the next thing that I'm going to do is take you through what the SDX HPLD system is, what it can do, and then I'll take you on a tour of the hardware and show you some footage of how it works. So what is this? What can it do? So what we have is this is an online intelligent automation system for dilution sample preparation of aqueous-based samples applied to inductively coupled plasma optical emission spectroscopy systems, but also some ICP-MS systems as well. Before sample introduction into an ICP-OES system, we can have a series of dilution modes that our samples and calibration standards have gone through. So first of all, we can have a situation where we've had no dilution. So our automation, our autosampler goes to a sample position and takes up a sample, no dilution process is applied, and it's carried through the system through to the ICP optical system. Then there's an option for a prescriptive dilution. So we can dilute a sample within a range of 2x up to 5000x. So from here, we can essentially generate our calibration standard solutions at different dilution factors from the same reagent tube, sample tube, and multi-element standard tube that's on the system. We can apply a blanket dilution factor to all of our samples. We can do what we like with our sample set. Then we have the last mode, which is a responsive dilution. So if any of our samples fall outside of certain criteria, it can trigger a responsive dilution where the ICP-OES system and the operating software calculates a more appropriate dilution factor that then brings the sample within the calibration range, and I'll be talking more about that shortly. And then this system, because a lot of sample analysis with ICP optical is time is of the essence, try and get through as many samples as possible. This system is compatible with our AS Express Plus rapid sample introduction system to increase the speed of this whole process. So what we use in this case, so instead of manually pipetting and diluting samples, we use a syringe pump module, which I'll get to shortly, to take up a sample aliquot and also a volume of dilution media, and then dispense that into a vortex vessel, which will then be used to mix, homogenize our sample immediately prior to sample introduction to our ICP-OES system. And we can do that in either a single dilution step or a serial dilution process. Now, because, again, we don't live in an ideal world, we have a scenario where we might also need to configure our wash process. We might be working with samples that have very high analyte concentrations, certainly if they're very unknown, they're unknown to us, we don't know much about them. So if we have very high analyte concentrations, we don't want to carry over issues, so we can configure our washout processes to make sure that after a sample's been diluted and introduced to the ICP optical system, we're now ready for another analysis, and there's no carryover from one sample to another. So we eliminate any kind of issues there, analyte memory effects from known analytes that have that kind of problem, so for the sake of argument, something like mercury or iodine. So we can configure the system to the analysis of interest. So just a note on dilution modes, I'll just go back to those briefly. So again, the first one, no dilution. So we can use our system to take up a sample from a sample tube, carry it through the system with no kind of dilution process applied to it, and it goes straight through to the nebulizer and spray chamber sample introduction apparatus of our ICP system and is carried on for measurement. So this is typically applied, it can be applied to blank solutions if the blank solutions has already been prepared, and it can be used for samples that have already been diluted or samples that don't require any dilution. That certainly might be the case in a water lab. So the next one I mentioned as well, a prescriptive dilution. So here we can apply a dilution factor per sample or per calibration standard. So we can give it a particular dilution factor and prepare from a certain source tube, a calibration line. We can apply the same dilution factor across the whole set of samples if we like, or different dilution factors. It's entirely down to the operator. So this is operator defined. We can work within a dilution factor range of 2 times up to 5,000 times dilution. So we can prepare our calibration range automatically from the SDX system, so there's no need for manual preparation. We can apply blanket factors or a mixture of factors. If we were so inclined, we could actually have a different dilution factor for each and every sample in a batch list if we wanted. And the last one we have responsive dilution. So I've already mentioned the issue of if we have a sample that contains an analyte at a concentration that exceeds our top standard, instead of incorporating error in our analysis of extrapolating that calibration line up to include the that sample which has passed the top standard, we can trigger a response to that, and the between the signal intensity for that analyte for the sample and the signal intensity for the top standard, a calculation is done within the software to work out a calibration, a dilution factor, so that the sample can be brought down into the calibration range. So typically, so we can set that, what that level in the calibration range can be. Typically, we set it so that a dilution is triggered to bring that sample to about the 60% level of the top standard. So somewhere in the middle of the calibration range, so it's not too close to the top, it's not too close to the bottom. So, and then that sample is reanalyzed in the same batch process. So it can be brought into reanalysis there and then when it's been recognized that it's not where we want it in the calibration. We bring that about, so that sample remains within any kind of quality control bracketing criteria that you might have. You might have a quality control sample every 10 samples, every 20 unknown samples, so it will fall within the same criteria. So you're not adding a large set of samples at the end of your batch, you're doing it there and then for each sample. And then we can also trigger a similar response if we have an internal standard suppression. So if our internal standard is suppressed, which therefore implies that the rest of our analyte signals are suppressed, if that signal is suppressed greater than the tolerance that we're interested in, for example, that might be 10%, then that can trigger an iterative redilution of the sample of interest until that internal standard is brought into tolerance. And then we can, from there, we will get the data that we want, and that can be applied. So that's the third type of dilution that we have on the SDX system. So what I'll do next is I'll just take you on a tour of the hardware, and then we'll start looking at how we apply the SDX into the workflow that I started discussing at the outset. So to start off with, this might look fairly familiar to some people on the call. So we start off with our ASX 560 autosampler. So this is the central piece of automation for the SDX HPLD system. So this is it's robust automation. It's our industry standard. This is a 4 sample rack autosampler. It's manufactured of molded polymer and carbon fiber components. There's no exposed metal. The internal boards are coated, so it's all about robust design and that it can be put in a harsh environment and it can still operate as it should. It's got high resolution XYZ movement, and that movement is also configurable. So our XYZ movements can be sped up or slowed down as required by the laboratory work. So we start with this automation. This is our focal point. This is what we put our samples on and our standards, etc. So now we add the SDX components. So the SDX high performance liquid dilution components. So what you'll see here is these are the components that we add on the right hand side of the screen. And we start off with, we've replaced the sample rack base tray. So this is how it differs to the standard ASX 560 system. We changed the base tray, and to that we are adding this vortex mixing module and some new standards positions. So you'll see there on the left hand side of the vortex mixing module there, that's our vortex mixing vessel. And then to the right of that, we have got 10 50 mil tube standard positions, which are reorganized so that they sit within that module and we're not losing any space on the system. And then added to that, we have a syringe pump module. Now this is what is responsible for aliquoting, taking up a sample aliquot, taking up our volume of diluting media that we need, and then dispensing that to towards the vortex vessel for mixing prior to sample introduction. So in terms of bench space, so there's essentially two sort of versions of this product. We have what you might refer to as the standard SDX HPLD system, which has the same footprint as an ASX 560 system, because that's what it is, with additional components. And you're only adding to your laboratory bench space this syringe pump module. And that's not even necessarily the case either, because what we can do is we can take that syringe pump module and we can mount it above the ASX 560 autosampler, so that you are still only now working within the bench space of the standard ASX 560. And then if you want to add the AS Express Plus, the rapid sample introduction from there, then you're only adding the components of the AS Express Plus there, which are typically sat next to the ICP optical system anyway, as close to the nebulizer as possible. So fingers crossed that this will work okay. So I've got some video footage here. I'm just going to show you the operation of an SDX system, just a basic process of how this system works. So hopefully this will come through. So what we'll look at here, that's the SDX syringe pump module. And in our laboratory in Omaha, Nebraska, what we're showing here is the ASX 560 with the vortex module in place at the back. And there's the syringe pump module sat next to it. And what we're going to do is we're going to show a basic sample introduction, and there's a sample in inverted commas there, some blue dye in one of the sample positions. So the syringe pump module, first of all, it does a priming process, and then it takes up an air gap. And then we're going to take up an aliquot of the sample into the sample probe. And then the sample probe is going to go for a dunk in the rinse station. The sample probe goes to the vortex vessel, and then the syringe pump module takes up a volume of diluting media, and then it dispenses the sample and the media into the vortex vessel, where it mixes. So whilst it's mixing, it's done its dispense, the sample probe goes to the rinse station, and then it goes back to the vortex vessel, and the sample is taken up and carried off to the ICP optical system. So that's done either under the power of the peristaltic pump that's on that ICP system, or it's pulled by our AS Express Plus vacuum pump. So it's essentially treating the vortex vessel like a sample tube. If there's any sample still left in the vortex vessel, afterwards it's then drained out of the bottom, and then some rinse media is pumped in through the bottom, and that vortex vessel is cleaned, and it's made ready for the next sample analysis. And then we're good to move on to the next sample in the batch list, or the next calibration standard, or blank, etc. So hopefully that video footage came through. So that's a standard operation of the system. So bringing the SDX system into the workflow. So we're now going to return to the idea of this workflow at the outset and talk about what the SDX HPLD system will do in terms of that workflow. So this is the workflow that I set out at the beginning. Essentially what I want to do next is I want to sort of cross off each one of these components where possible that the SDX addresses. So I'll take you through this. So essentially, I'll just talk through all of these. I've put a line through each of these aspects of the workflow that the SDX essentially covers and removes the need for essentially laboratory staff effort. So starting off with the sample again, if I start off with the sample in red on the left-hand side of the screen, you might need a sample digestion if you've got a solid sample. That's not always the case. But so if we park that digestion for a minute, because the SDX doesn't handle that, but it can work with digested samples. So the SDX will cover general sample dilution. It's going to cover the preparation of your QC samples. It can cover the preparation of your blank samples, because essentially you can take water as a 18.2 megaohm water as a blank, dilute that with a low concentration acid solution, much like it would do any other sample or calibration standard. It will cover your calibration standards, so all of that is handled. Automation, the automation is all there to lead into the sample introduction process before we get towards going through the measurement process on the ICP and data generation. After the data has been generated, if there is any issues there where you've got analyte concentrations that exceed your calibration, internal standard suppression, essentially the SDX system is going to handle that and will then bring everything back around in a circle. So essentially what we're doing here is if you have that issue, then it will recycle back through the redilution process. It will trigger one of those redilutions and essentially bring everything back so that you generate the data that you want. So we're removing the need to do a full reanalysis, batch analysis. So if what I typically used to do, when I was working in the laboratory, was I would do my sample preparation in an afternoon, run my samples through the night, and address my and assess my data the following morning. In this case, if you were using the SDX system in that kind of scenario, then you could leave the SDX to do all of the prep. You could have done your work through the day. You could put your samples in your sample racks, essentially rack up and leave. Put the get the SDX started. Have all of your dilution factors in the operating software. Start your batch. It could have done all of the preparation, all of the analysis, and any reanalysis that was required, and then you come back and you know that your samples have been analyzed and you don't need to do any reanalysis. So the whole process here removes the need for that batch reanalysis unless you have some sort of QC failure that is outside of your criteria. So SDX compatibility, that's what I'll move on to just briefly on this. So as it currently stands, as of March 2021, so the SDX system is compatible with Thermo's Qtegra operating ICP-OES platform, and also Spectro's ICP-OES platform that operates with ICP Analyzer Pro. We do have another platform that's pending imminently, and there's also a further two beyond that we are working on, that we're looking for launch in 2021. So we're looking to broaden this compatibility, and then there's other options that we're looking at following 2021. So there will be more ICP optical systems that will be compatible with the SDX system over the coming year. So, water analysis. So this is after going through everything with the SDX system and the idea of the workflow. I'll be referring back to the workflow again, but after going through this, I want to apply this to wastewater analysis. Now, water analysis is one of those near universal things. It's a very global analysis. Every country in the world has some form of water testing. So I'm going to be speaking specifically to wastewater analysis, but the SDX could similarly be applied to any other kind of water analysis and many other applications as well. And there is another webinar that I'll be delivering next week, where I'll be focusing more on things like samples, solid samples, digest samples, and food analysis, that kind of thing. So wastewaters. So wastewater, discharged, untreated wastewaters, effluents, etc. One of the common ways to approach this is to release them into the environment. Now, these can cause harm to the environment. There can be economic harm as well. Certainly, if these water samples contain, or these waters that are discharged, if they contain high concentrations of toxic metals. So around the world, it's certainly the case in the EU, it's certainly the case in the USA, it's certainly the case in many other countries. There is legislation in place that dictates that these effluents, these discharged wastewaters, they need to have been tested, analyzed, and made safe before they are released into the environment. So these waters, these types of samples, water samples generally, these are the kinds of samples that can be, if they, as long as they don't contain a lot of particulate material, a lot of high TDS, typically they can be nebulized and introduced to an ICP optical system without any further pre-treatment, any further dilution. So, but there's a problem here with this kind of sample, and that is that depending on the industrial process that these waters are coming from, the analyte composition can vary quite widely, and also the analyte element concentration can vary quite widely as well. So one of the challenges there is it's harder to calibrate against that, not knowing what the calibration range needs to be for different analytes, etc. So that's an immediate problem if you want to just nebulize these samples straight to an ICP without preparing them or without diluting them further. So what I'm going to do is essentially I'm going to theoretically, and we have done this work as well, so we've practically done this, apply the SDX HPLD system to this scenario, to this suggestion. So just sticking with this problem, which I highlighted on the previous slide, our water analyte composition varies, our analyte element concentration might vary as well. So using the SDX HPLD system, we're going to take advantage of the different dilution modes for this kind of scenario and arrive at this idea of rack up your samples and leave. So take your samples just put them in sample tubes, put them on the ASX 560 autosample that's at the center of the SDX system, start your analysis and leave. So with the SDX, we're going to take advantage of the prescriptive dilution mode for preparing calibration standards. You might also be using that for preparing your blanks, if you haven't pre-prepared your blanks, and also for preparing your QCs. We can use the dilution mode if we wanted to for the samples, but in this case we won't, because we don't know what the composition is, we don't know what the concentration ranges are going to be. So we'll just run them in the non-dilution mode and pass them through the system, and then we'll use the responsive dilution modes. So if these samples contain analytes that are at concentrations that exceed the top standard, then that will trigger the responsive dilution and bring those samples back down to within the calibration range. And then we can apply the same for the internal standard suppression from the sample matrix if that's also an issue. So essentially what we're doing here is we're using the SDX to remove the unknown of the sample composition and the unknown of the sample element concentrations. So the system will respond and redilute, reanalyze these samples without the interaction of the laboratory analyst. So that's how we get to rack up your samples and leave. So I said that we practically applied this, and we have. There is some work that we did with Thames Water in the UK and with Thermo site in Hemel Hempstead. We did this work with them, and there was actually a conference poster which we've presented previously on this. So we used our SDX HPLD system, Thermo's ICP optical system, and a Miramis nebulizer. We used this system from a multi-element stock solution, we used this system to prepare our calibration standards, a calibration range, and we factored in 5 ppm yttrium internal standard. And for this work, our samples were Thames Water provided us with 15 unknown wastewater samples, so we have no idea what the concentration ranges of the analytes might have been. And then we also added for quality control in this 2 aqua check samples as well, which we didn't apply any dilution to either. So we've treated those as samples. So just to show you some data, I'm not going to focus on this, but just to point out there's 15 or 16 analytes there, analyte elements that we're interested in. We did a series of dilutions on a multi-element standard stock solution. So we did 100x, a 20x, a 10x calibration, used a blank, and then we've got a 4-point calibration line there. And then we had an AQC standard there as well for quality control. So we applied the SDX to these samples. As I've already mentioned, the calibration standard blanks, QCs, and samples, they were introduced to the ICP through the SDX system. Our calibration standards were prepared. We have our lines, we have our blanks, our QCs, and then we ran the samples through. Now, of the 15 completely unknown wastewater samples, 10 of them showed they exhibited analyte concentrations that exceeded the top standard. So 10 of those triggered the responsive dilution to bring them down into the calibration range that we wanted. So basically, we've reanalyzed those 10 within the same batch without having to repeat sample preparation, without having to repeat an analysis, without having to come back to the system again the following morning, etc. We've avoided having to do that. And then the responsive dilutions associated with those 10 samples fell to something like we needed something between either a 2x or 140x responsive dilution to bring those samples into calibration range. And then again, just to show you some more data, I don't want to dwell on this either, but the thing that I did want to point out from this data set was the dilution factors involved here. So what you've got, if I just start at the top, the AQC QC sample did not require a further dilution. So with that fell within the calibration range. So that had a dilution factor of 1x. The subsequent QCs and samples, this is not all of them, this is just some of them, that needed a redilution. Those are the dilution factors that were calculated by the system and then applied to those samples as for the reanalysis, so that data was then generated from there. So that's what I wanted to point out from this data. And then essentially the conclusion of for this application, and this is sort of where I want to finish today, is that the SDX system has enabled the automated prescriptive and responsive dilution for this sample set. So it's allowed the laboratory analyst to avoid, first of all, an incorrect quantification. So those 10 samples which exceeded the top standard, that might have been a criteria of your analysis. So your criteria might be to extrapolate, but it's allowed the analyst then to do a reanalysis, bring everything down within the calibration range and avoid an incorrect quantification or a quantification whereby there's that question of error associated with it. It's also avoided the need to reanalyze the whole batch or to reanalyze a small number of the samples, but also with the calibration standards that you need, the blanks, the QCs, etc. So basically, it's avoided the reanalysis, but the associated, the cost of doing that, the cost of the reagents, the argon, the staff time, the time of somebody doing it, and the effort of somebody doing that analysis again. So essentially, productivity can be improved through this approach because you don't have laboratory analysts just continually doing preparation. You've got an improvement in accuracy and precision and minimizing error. So that's the conclusion that I want to get to after having gone through the analytical workflow, the SDX product, and then applying that to this scenario of wastewater analysis. So like I said, you can also extrapolate that to other water types, other sample types. The SDX can be very broadly applied in ICP-OES analysis. So that's where I wanted to end it today. So I feel like I've whizzed through that. So thank you everybody for your time and your attention. Please feel free to send through any questions that you might have on the SDX system or any questions that you might have on certain sample types, etc. Please feel free to email those questions to me or to Teledyne sales, and we can answer those questions from there. So thank you for your attention, and I will call it there for the day. Thank you.
Thank you, Pete. Have a great day, everyone.